In this video, I want to walk you through some sample data and some conclusions we reached from our ramp lab. In a ramp lab, we investigated objects that change their velocity, and specifically, we looked at how the position changes and velocity changes for this spinner that's increasing in speed while it's moving in the positive direction. In this lab, we ended up collecting the position of the spinner for each and every second it was moving down these pipes, and then we used that position versus time graph to figure out how fast the spinner was moving at each individual instant in time, called the instantaneous velocity, and then we made that velocity versus time graph. For our conclusion discussion, we looked a lot closer at trying to figure out what the velocity versus time graph was telling us and what new information we could learn. We also came up with an equation to represent how velocity is related to time. In class, each lab group made a whiteboard of their velocity versus time graph. They added a linear fit if it was linear, and all of them ended up being linear, so then each group was also able to write the equation for their linear relationship. Here's just a couple sample whiteboards of our results. The velocity versus time graph, resulting equation. Here's another group, their same linear graph and resulting equation. These two velocity versus time graphs and equations are pretty representative of the data we saw in our conclusion discussion. So the first question was, what was similar between the graphs? Well, we figured out that in all cases there was a linear relationship between the velocity and time. As time went on every second, the velocity increased by the same amount. And so there was a linear relationship. The differences were we didn't all have the same slope. So we noticed that, like in this case, this spinner had a slope of 0.95 centimeters per second for each second, and other spinners had steeper slopes, had higher slope values. And so naturally we asked, well, what does that tell us differently about the spinners? Well, since this is a velocity versus time graph, the slope represents how much the velocity changes for each and every second. And if some spinners had higher slopes, that means they must have been changing their velocity by more each and every second. And we noticed that the groups that had higher slopes also had ramps that were actually steeper, which makes sense. If you have a steeper ramp, every second that goes on, the velocity we would expect to increase more and more each and every second. So we said the slope just represents the change in velocity for each and every second, and those spinners that had less steep ramps were changing their velocity by less each and every second. Another thing we noticed was that the y-intercept values were a little bit different. And so in this case, the y-intercept was 0.65 centimeters for each second. In this case, it was 0.11 centimeters for each second. But we noticed that they're all fairly small values. Like here, you can see on the graph, it crosses pretty close to 0. And relative to this data set, it also crosses fairly close to 0. And we thought, well, what would we expect the y-intercept to be? Would we expect it to be 0? Would we expect it to be non-zero? This is the intercept of our line of best fit, so it may not be perfectly representative of reality. So we talked about a couple different ways that we could think through what do we do with the y-intercept if we expect it to be 0. So the question is, shouldn't the y-intercept be 0 in this case? It's pretty close to 0. Well, there's two different ways that we can deal with that. One is we can kind of look at the range of y values, or in this case velocity values. We can see that in this case the biggest velocity value is about 9 centimeters per second. When we look at the y-intercept, 0.65 centimeters per second, that's quite small compared to our biggest y value. So we say, is it close enough to 0? Well, the way that we're going to judge that is we're going to use something called the 5% rule, and it just states that if the y-intercept is less than 5% of the maximum y value, which in this case was 9 centimeters per second, then we can say that statistically it's pretty insignificant compared to our whole data set in terms of y values. If it's less than 5%, we're going to say it's small enough to basically be 0. But if you do this in a lab report, you have to make sure that you include specific values to show that it is less than 5%. So let's do that for this sample data set. What is 5% of the maximum y value? Well, their maximum y value is 9 centimeters for each second. So to find 5% of that, we multiply it by 0.05. That turns out to be 0.45 centimeters per second. That's 5% of the biggest y value. Is our y-intercept smaller than that? Turns out that in this case, with this data set, our y-intercept, that value, is bigger than 5% of the biggest y value. So in this case, we actually can't appeal to the 5% rule to say that our y-intercept is insignificant. But we talked about, like, what would we expect our y-intercept to be? Well, on a velocity versus time graph, the y-intercept is the velocity at time 0, or the starting or initial velocity. And in all cases, we started our spinners from rest, and then we let it go and we let it start speeding up down the incline or the ramp. And so they should be 0. If the 5% rule can't work to say that the y-intercept is insignificant, then we can just use logic. If you can reason that the y-intercept should be 0, you can just say that it's 0, even if it's greater than 5% of the biggest y value. So in this case, we said the velocity of the spinner actually was 0 when the time was 0, and so we can just say the y-intercept is 0. So if we take our equation, we can either cross that out and just say that, in this case, the equation would be velocity equals 0.95 centimeters per second for each second, multiplied by time, or you could just write the equation like this, where the y-intercept is 0 centimeters per second. Now that we understand what the slope and the y-intercept represent about the motion of the spinner, we can come up with a general equation which describes how the velocity changed for all of our spinners. Right? We just had slightly different slope values and slightly different y-intercept values. So with the slope, we said that we thought it represented how much the velocity changed each and every second. It went up by the same amount each and every second. And in physics, we actually have a word for that that's called acceleration. So the slope of our velocity versus time graph is acceleration. It's how much the velocity changes each and every second. So the symbol or variable we use to represent acceleration is to the lowercase a. And in our lab, the units of our slope was centimeters per second for each second, how much the velocity units changed each and every second. When we talk about this later in class, the standard units for acceleration are not centimeters per second for each second, but it is meters per second. So we measure velocities in units of meters per second. And so acceleration has units of how much the velocity units in meters per second change for each and every second. Sometimes you'll also see this written as meters divided by seconds squared, because this complex fraction simplifies to just something like this. In the future, though, I would encourage you to write the acceleration units like this, because it's a visual reminder about what the meaning, the conceptual meaning of acceleration is, how much the velocity units change for each and every second. Looking at the y-intercept, we said the y-intercept represents how fast the spinner is moving at time 0, or its initial velocity. So the similar variable we're going to use to represent that is v sub 0, kind of like we did for initial position, which was x sub 0, and the units for velocities will typically be in the future meters per second. So let's now replace the number and units for the slope and the y-intercept with the symbols which represent what it means. So our general equation, it's an equation that includes just symbols. There's no numbers or units, just variables. And so it looks like this. Final velocity is equal to the acceleration of the object multiplied by time plus the initial velocity. So now we have an equation which allows us to figure out how fast something is moving if we know its acceleration, how much the velocity changes each and every second, the time it's changing its velocity for, and what was its initial velocity. But before we plug numbers into here, I want to think just a little bit about the acceleration. In this case, in our lab, was the acceleration constant? Remember, acceleration came from the slope of our velocity versus time graph. And if we go back to a couple examples of those graphs, we said that there was a linear relationship between velocity and time, and the slope of any line is by definition constant. In each case, the velocity was changing by the same amount each and every second. And so in this equation, the acceleration value, it was constant. And to use this equation, we can only use it for situations where the velocity does change by the same amount each and every second, where the acceleration is constant. Or another word we can use for constant or unchanging is the word uniform. So we could say here that it has a uniform acceleration, a constant acceleration, or it changes its velocity by the same amount each and every second. So in an introductory physics class, this is the form of the equation that we would use. If you're in an AP Physics 1 class, The equation looks a little bit different on your AP equation sheet. It's very similar, except there's a couple subscripts on 3 of the 4 variables. So v sub x, a sub x, and vxo. So vx stands for the instantaneous velocity at some specific time, whatever time you plug into the equation, or you can think about it like the final velocity. A sub x is acceleration, and vx0 is the velocity at time 0, or the initial velocity. And a way to make sense of this is you can just think that these subscripts are reminding us that the velocity, the acceleration, and the initial velocity, they all have to be in the same direction. You might think, well, why does that matter? Well, in this case, we're talking about one-dimensional motion. It's motion in a particular direction, in this case, down the ramp. In the future, in this class, we're going to be talking about two-dimensional motion, and we'll be talking about, vertical velocity versus horizontal velocity. And so we'll end up using this equation down the road, and this is just reminding us that whatever we plug into this equation all has to be information about the same direction of motion. One last thing before we're done with the video is if you guys have to write a lab report and you have to define any new terms that came up in this lab, there was 3 of them. The first was instantaneous velocity, the velocity of an object at specific instants in time. The second new term was acceleration, which came from our understanding of the slope, which was the change in velocity each and every second. And then the last new term was uniform, which just means constant or unchanging.